Alexander Goncharov from Yale University. His title is Quantum Symmetry from Quantum Geometry on Moduli Space. Welcome.
Thank you very much for the invitation to the conference and for the possibility to come to this beautiful place in China. So my talk is based on a joint work with Linhui Shen and continuous work with, it's a continuation of work with Vladimir Falk. So from Galois-Einstein, the idea of symmetry plays a key role in mathematics and physics. And after works of Young and Baxter, the idea of quantum symmetry emerged in the 70s and 80s in the works of Leningrad School, Fadeev, Sklyanin, Takhtajan, Reshetikhin, and precise form was discovered later by Drinfeld and Jimba. So what is quantum symmetry? When we talk about usual symmetry, we have a group or Lie group acting on a set on a space X. And when we have a quasi-classical variant of this, then groups and spaces and maps become Poisson. So according to Drinfeld, a Poisson Lie group is a Lie group G with a Poisson structure, such that the inverse and the composition maps are Poisson. And there is a new aspect that any Poisson Lie group G has its dual, which is also Poisson Lie group called G star. Now, proceeding according to ideas of quantum mechanics, the algebra of functions on a Poisson space should be quantized to a non-commutative algebra, or Q of x, depending on some parameter Q. And Poisson action G cross x to x should be quantized to a map of the algebras of functions in the opposite direction. And so if G is a Lie group, then the algebra of quantized functions on G should become a Hopf algebra. So, for example, we get universal quantum enveloping algebra by quantizing this way as a group G star. So the simple example is universal enveloping of SL2, which is the algebra generated by elements E, F, and K with relations that the commutator of E and F is Q inverse minus Q, K minus K inverse, and that K group X on E by conjugation with eigenvalue Q square, and on F with eigenvalue Q2 minus square. So I was about to say this one. So this is not exactly standard kind of generators, because I have to normalize to get in the quasi-classical limit, not U of G, but functions, commutative algebra of functions on G, and that's why they were normalized. Now, this algebra appeared first in the work of Kulishin Reshetikhin in 1982, and there is also explicit coproduct which was discovered later, which makes it in a Hopf algebra. And so it is highly non-trivial to define even simplest Poisson Lie groups, and therefore quantum groups, for the following problem. So to define what is a quantum symmetry, we first have to break the symmetry. For example, to define a Q of SL2, we have first of all to choose a basis in two-dimensional space, and then basis produces linear basis in SL2, and then we quantize this basis. So in the case of, let's say, work of Kulishin and Reshetikhin, where this algebra appears, it was natural because they were talking about spin chain. But the name quantum group, which was suggested by Drinfeld, assumes that we should have quantum symmetry group. And that's a kind of, looks like a contradiction, because it's very strange to define symmetry by breaking symmetry first. So I would like to, in this lecture, to discuss a more geometric approach, explaining that quantum symmetry arises naturally from quantum geometry of moduli spaces of G local systems on surfaces with boundary, which we call decorated surfaces, equipped with some extra boundary data. And the key role in the quantization and even in definition of Poisson structure plays a notion of cluster Poisson structure. So we are not going to see R matrices and stuff like that to proceed. So rather than that, we'll be talking about cluster Poisson structure on these moduli spaces. So as an input, I take a split semi-simple algebraic group over Q, which usually, often I would say, will be adjoined, for example, PGLM. And S is a decorated surface, meaning it's oriented surface with boundary. and punchers. And on the boundary, we have special boundary points, which I call corners. So for example, on this picture, you see that we have 2 punchers, blue, and we have 3 boundary components, punctured red, and we have 5 corners which appear as these 5 red points. Again, so I picture this as kind of polygon, but on the picture it's round, just the points. So they're corners. Everything modular isotopy. Now the output is a certain moduli space, call it PGS. So it parameterizes geolocal systems on the surface with boundary data, which is of crucial importance. The boundary data includes a flag B near each puncher, which is invariant under local monodromy. This means that I take a point nearby of the puncher, take a flag at this point, and insist that if I go around the point, then the flag comes back to itself. It's an additional structure. And at the corners, I just choose a decorated flag. No conditions on that. Except that if I consider a boundary interval, for example, on this components where you see 2 points, there are 2 boundary intervals. If I consider just one of them and transport the flags to the center, then I will have 2 flags there, and I insist they're in generic position. So that's a precise definition of this step. Now, let me just recall that the flag variety parameterized Borel subgroups, so it's G mod B, and decorated flag variety, which will play decisive role in kind of all discussions, this is G mod U, where U is a maximal unipotent. For example, for SL2, you get projective line and a fine line minus a point. And so in this example, if you talk about moduli space related to SL2, then it parameterizes 2-dimensional flat symplectic vector bundles on the surface with monodromy invariant line near each puncher and non-zero vector in each corner. And vectors at the corners, which are on the same boundary segment, supposed to be non-collinear. So the key feature of this definition is that there is a gluing map. First of all, you can, of course, glue the decorated surfaces. If you have 2 boundary intervals, which are punctured red on the picture, then you can glue them together and get a new surface. So for example, here from 2 triangles, you get a rectangle. This surface inherits decorations. It inherits corners and punchers. Now we can define the corresponding gluing map on these moduli spaces. So in order to glue, I have to introduce a notion of pinnings. And it's a little technical, so you have to understand that this is just analog of frames in a vector space. So for example, a pinning for PGLN is just a projective basis in a vector space of dimension n, given by a basis considered up to rescaling. And from the technical perspective, pinning is just a pair of decorated flags NY and A1, A2. And when you have such a pair in generic positions, then there is some invariant which takes value in the Cartan group, and pinning is such a pair where this invariant is 1. So the key point that the group GX freely transitively from the left on the pinnings, and another point is that if you have a generic pair of decorated flags, for example here, then it determines spinning on every on all boundary intervals here. So here we have 1, 2, 3, 4, 5 pinnings because we have five boundary segments. So we have pinnings at all boundary intervals. And now we can glue. So how we glue? So if you have 2 boundary intervals, we consider our geolocal systems in vicinity of these boundary intervals. Then there exists unique map to identify these geolocal systems, which are trivial, but here, in such a way that one frame goes to the other frame, one pinning goes to the other pinning. A little caveat that to get the correct space, we have to identify one pinning with opposite pinning, opposite obtained by just interchanging A1 and A2. Then we get a correct way of glue, which we need. Okay, so that's the moduli space. It comes with a feature of pinning. But it also has another important feature. It has a huge group of symmetries. Well, first of all, the mapping class group gamma S acts on everything. preserves the decorations, and so it produces action on the moduli space. Secondly, at each puncture, there's a Weyl group action, which is birational, on this moduli space. Let me explain how this works. So if you consider just this puncture, for example, for PGL2, then if you go around, you get a monodromy map. So it's a map of two-dimensional space to itself, and has two eigenlines. And the definition involves choice of one of them. But you can choose the other, and that's Z mod to Z action. Or in an n-dimensional case, you have n eigenlines in general, and if you order them, you get a flag. You can choose a different order. That's the action of the symmetric group. So that's the action of the Weyl group here. Then, if you go to the boundary component, then on each boundary component, there is an action of the braid group, which I'm not going to discuss, just want to say that it is there. And finally, the group of automorphisms of the group G obviously acts on everything. These actions are almost commuting, and precisely the semi-direct product of these groups acts naturally on this moduli space. And so the first main result is that for adjoint split semi-simple group G, this moduli space PGS has a gamma GS equivariant cluster Poisson structure. So what is cluster Poisson structure will be explained in a minute. But before that, I want to say that this was proved first for GLM in our work with Vladimir Fogg 20 plus years ago, and we got just equivariance with respect to the mapping class group. Then this was extended in the case-by-case study by Inle in 2016, and also since he treated D4 and used faultings, he got also G2. And then the final version was in our paper with Linhui Shen for any group G, and it was simultaneous, I mean, kind of not a case by case, but simultaneous general construction, and even more flexible than we originally had it with Fogg for PGLM, which turns out to be important. And the whole group gamma GS was equivariant. The structure was equivariant. But now back to the question, what is cluster Poisson structure? So a cluster Poisson structure on a variety X is determined by extremely simple data. You just choose a collection of rational coordinate systems Xi and a skew-symmetric matrix with integral values. Then you can define a Poisson structure on an part of your manifold by postulating that the Poisson brackets of those coordinates xi and xj is epsilon ij xi xj. Why Jacobi identity is satisfied? Because if you take the logarithms of these xi's, there will be the constant Poisson bracket obviously satisfies the Jacobi identity, and therefore it satisfies for those as well. So we call this data Poisson cluster. So again, Poisson cluster is a collection of coordinates and a skew-symmetric matrix. Then it can be mutated in the direction of any of those coordinates, and we get a new cluster, which has a new coordinate system and new Poisson tensor. But in such a way that if you produce this Poisson structure by the same formula, the Poisson structure actually is the same. It just its description changes because we got a new coordinate system and therefore a new epsilon ij tensor to get the same Poisson structure on the manifold. And then we can repeat these mutations up to infinity. Now, this looks similar to Fomin-Zelivinsky cluster algebras, although it is different. So the similarity is in the sense that this epsilon j matrix mutations produced the same way. Actually, they were discovered by Zyberg in '95, even before the story, this part of mutations. But then the mutation rule for coordinates is different. And another feature is very important is that in general, if you talk about cluster algebras, they in general do not possess Poisson structure, in spite of what one might think, in the sense that if you want to have gamma equivariant Poisson structure, then usually there is none. If you take one cluster, there is a plethora of Poisson structures which are compatible with cluster algebra structure. But if you want to have equivariance, usually there is none of them who survives the equivariance condition. Okay, now what kind of conditions this forces on us? The very existence of rational coordinates on xi forces x to be rational. For example, the claim that we have cluster Poisson structure in this theorem, I claim that this moduli space PGS has cluster Poisson structure. This implies that it's a rational variety. If you just look on moduli space of local systems on S, it's usually not a rational variety, not even unirational variety. But this kind of moduli spaces, they're always rational. That's number one. Secondly, you can ask what kind of restrictions you have on matrix epsilon ij, and the answer is none. So you can take any matrix for given any coordinate system, rational coordinate system, you produce cluster Poisson structure. Is that good? Well, the main thing is that you usually come on a moduli space, like in our case, where the underlying Poisson structure is supposed to be equivariant under a huge group. And if you want to impose condition that you found some cluster Poisson structure which is equivariant, this is extraordinarily strong condition, and it's not clear at all why a single one exists. Because this boils down to the following condition, that for any element of your symmetry group gamma, you can take your cluster, meaning it's collection of coordinates, you can pull it back, get another cluster, and the condition is that this new cluster is mutation equivalent to the old cluster. It's not clear how to do this, it's not clear why you can do this. So in general, as I said, it is extremely surprising that we do have equivariant cluster Poisson structures. As you will see, this equivariance is actually key for the whole story. Now, if you do have cluster Poisson, it will be in the second one, quantum algebra. I'm just coming to that. So what's the benefit of this cluster Poisson structure if you have it? There are two crucial benefits. First of all, you can consider Q deformation of the algebra of functions, OQ of x, on x. That's, I think, Vanya, was your question, right? And secondly, we can quantize, this is cluster quantization, where we produce a representation of this algebra by unbounded operator in certain Hilbert spaces. This will be discussed in a few minutes in detail. And as Vanya was suggesting, this whatever we do is equivariant. For example, the group gamma is going to act by automorphisms of this cluster algebra by the very construction. Okay, let's go first to question how we deform the algebra. So a cluster means collection of coordinates in a tensor. It produces quantum torus algebra, which is just the algebra of non-commutative polynomials in X and an even inverse modulus the one relation that xi xj is q to epsilon ij xj xi. And I emphasize that q for me is not a formal parameter, but an actual number. Now, if you want to consider mutation in the direction of one of the variables, then I have to produce isomorphisms of the fraction fields of the corresponding quantum torus algebras. And remarkably, you need just one device for that. So this device is a quantum logarithm power series, which are defined as follows. You take this 1 plus qx, 1 plus qqx, 1 plus q5x, and so on, and then you invert it. So it's just a power series. If q less than 1, absolute value of q less than 1 converge, but usually it's just a power series, so it's not a function. Then we use this as a device as follows. Okay, what do we want to do? If we want to take one coordinate system with coordinates xi, and we want to produce another coordinate system with coordinates xi prime. And so the first thing you do, you consider the conjugation by this quantum logarithm power series. Xi goes to psi q of xk, xi psi q of xk inverse. So usually when you conjugate by power series, you get something which is again a power series. In this case, you get a birational map. This is due to special difference equation for this quantum logarithm power series. By the way, this quantum logarithm power series, they were known in 19th century under the name of Pohammer symbol or Q Pohammer symbol, and some people refer to them as Q gamma functions. Some other people say that this is a Q exponential function. So this power series has many relations to different interesting objects. Okay. Now, after I do this conjugation, it's not exactly the end of the story, because I need to apply to this some simple monomial transformation, which I'm not going to bother to tell you what is this. I just want to tell that this simple transformation encodes actually this mutation rule for the Poisson tensor, some linear transformation. Okay, now we can define what is the algebra. The algebra of Q of x consists of this quantum Laurent polynomials f in a given coordinate system, meaning which belongs to given quantum torus algebra, such that after any sequence of mutations, the mutated rational function is still quantum Laurent polynomials in the new coordinates in the new cluster. Okay, so that's the story about this OQ of x. After this definition, it's not clear at all why there is a single element in this algebra except a constant. The constant is always there. To produce any other element in this algebra, it's a challenge. This is also different from the cluster algebras, which do have lots of elements by Laurent phenomenon series. This is not quite the case here. Okay, but now we go to the properties of these algebras, which we get by assigning them to our surfaces. And Faddeev famously said that quantization is an art rather than a funter. So in this case, I claim that we got a funter. And so the claim is that for any adjoint group G, we have a funter from the category of decorated surfaces, where the morphisms are inclusions. And this funter assigns to a decorated surface S this quantum algebra or Q of PGS. So once again, your input is S and G, and then you get some algebra. And then functoriality amounts to the following, that first of all, the group of diffeomorphisms of X on everything, and I claim that it also acts on OQ PGS through the mapping class group. So that's functoriality under diffeomorphism of S. Then there is action of the Weil, braid, and out G groups. So they act by symmetries of this funter. And then there are also maps of a surface to a bigger surface. And the typical one, if you just delete a loop from a surface and embed it to the original surface, it's quite non-trivial, very non-trivial fact that we have functoriality in this case as well, on this quantum ring. And on the top of this, there is another property which is crucial for us of this gluing maps, that they also contravariant functorially for the gluing maps. So what does it mean? That if you have a map which is gluing of your surface to a new surface, a map on surfaces, then we have a dual map on the moduli spaces. But then we have also map, again, the other direction, on the algebras of functions and on quantized, that's the claim, on the quantized algebras of the functions. And so that's why it's I get confused by functorialities anyway, forgive me this. So you get natural functoriality for gluing maps. Okay, now I'm going to proceed to what I promised, the quantum groups via this technology. But first of all, I need one more definition. So I'm talking about this moduli spaces PGS. But actually, in many cases, I need just moduli spaces of local systems on the surface. If your surface just surface with punctures, this is a plain local systems we know. But if your surface is like a polygon, then there are no local systems except trivial one, but we still have very good moduli space, very rich moduli space. So there is some kind of notion of a true moduli space of local systems on a decorated surface, which is not exactly what we used to in this situation. And as I said, I cannot introduce immediately quantized functions because this is usually non-rational space, sometimes non-rational space. And the definition is that we use the action of the Weil group at the punctures to impose equivariance, just to take invariance under this action. And then we get some subalgebra. That's by definition the quantized algebra of functions on the surface. So here we use crucially the fact that the Weil group acts by this cluster Poisson transformations. Otherwise, I wouldn't be able to perform this operation. Okay, so what is the first example of the situation? We can take a surface which is a punctured disk, and this punctured disk comes with a puncture and with two corners, which are two special points. And I claim that if you consider the corresponding moduli space of G-local systems, so this will be G-local systems. I forget about flag at the middle already because I'm talking about local systems. But then I have decorated flags here and here. That's my moduli space log G. And I need to reduce it in some very simple way, which I'll explain later. This is mu equal 1 condition. Don't worry about this for a moment. But if you just have this picture, I claim that the corresponding moduli space will be canonically identified with the Poisson Lie group G star. Why? Because if you have two surfaces like that, two decorated surfaces, you can glue them, you have this boundary component and that boundary component. You can glue them together on a surface. So you get a new surface where you have two punctures and what remains, the seam which remains after gluing. You ignore the seam, but then you also have two punctures, you enclose them, and so you cut them out, so you get just a single puncture. So that's the operation by gluing and encircling. And this operation is a group law. It's basically immediately clear that this operation is associative. Just if you take 3, you glue this and then that or that and this, it's the same. You get the same thing because you, in the end of the day, encircling everything. You can also define inversion just by flipping the surface. And there is a unit, so it's on the nose Poisson Lie group. And I claim it's canonically the one which is called G star. So for example, the Poisson structures coincide. But I want to stress that in my definition, to define the Poisson structure, I just have to produce this cluster Poisson structure in a single cluster, and then it knows itself, so it produces a Poisson structure, which is actually on the whole object, and that's the way we describe it here. Okay, one more example. So, sorry, I wanted to say that what is this mu equal 1 condition? Yes. We don't have, so that's it. Thank you for the question. So we have Weil group acting on the punctures, but I'm now talking about local systems. This means that I forgot about frames, or I just forgot about flags. No flags anymore. So when I said local systems, this means no flags anymore. So the algebra of functions is a sub-algebra because we effectively take the quotient. Okay? Otherwise, I would not be able to perform the gluing because there is no way I can assign a flag. If I have flags here, there will be no canonical flag here, and I don't need this. So I want to say that at every corner, it turns out that there is some invariant with values in the Cartan group, which I'll define a little later. And the condition here that a product of this invariance, 1 times W0 of the other, has to be equal to 1. Okay, next example. Let's talk about Poisson Lie group G. Then I claim this is going to be the moduli spaces related to a square. But it is slightly different, slightly more general than the one I was talking about before, because usually when we have a polygon like a square, we have 4 pinnings. And now I won't just forget about 2 of them. I want just to keep 2 pinnings, vertical ones. So it's a little modification of my previous moduli space. So it's a square with 2 pinnings. These 2 pinnings allow me to glue the moduli spaces. And so exactly the same way I can glue 2 squares with pinnings, then I get this kind of rectangle which has too much data. It has this extra points in the middle of horizontal segments, and I don't need them, so I can cut them out. After I cut them out, I get again a square. And so I claim that's a structure of Poisson Lie group, so it's on the nose associative. You easily introduce the inverse and identity, so you get the Poisson Lie group. The claim is it's canonically G. How do you see it canonically G? Because if you take one pinning here, you can parallel transport it to the other pinning. And then you have on the same spot 2 pinnings. This means you have element of the group G. That's the isomorphism. Okay. Now, next example, Drinfeld double of the group G. And so I claim that you have to consider again a square, but with a puncture. I have to consider local systems, so there is no flag at this puncture. And I want to have two pinnings at this vertical red sides of the square. And the composition law, again, as before, so you take two squares like that, you glue them along the vertical sides which look at you, then you get a new surface with two punctures and three corners, three great points on each side, which is overkill. So you encircle the punctures, so you get just one, and you cut out this intermediate corner, so you get precisely the modular space you start from. So that's again the composition law, and it's obviously associative on the nose, and so it produces some Poisson-Lie group, and I claim it's canonically Drinfeld double. So this way I can produce lots and lots of different Poisson-Lie groups just by looking at surfaces and playing with the gluing and encircling. But now, since I have any of these Poisson-Lie groups, I can apply this functor, so I can produce algebra of quantized functions. And so it's supposed to be a Hopf algebra. And so the question is, what kind of Hopf algebra? So I just repeat that in the case of this disk with a puncture and 2 points on the boundary, 2 corners, we get G star. And so it's natural to think, if you think about this, what kind of Hopf algebra is supposed to get? Of course, it's UQ of G because you got G star. But then comes a fundamental question which you ask yourself, okay, so you get something which is on the nose Poisson-Lie group, so it's supposed to be Hopf algebra, but what it has to do with UQ of G? No. Vanya, very good. So let me go back to the main point. When I'm talking about cluster Poisson structure, this means that I have some space and it carries cluster Poisson structure. This means that you have some cluster, some collection of coordinate system on your space with Poisson tensors, which is usually never canonical, just take some. And then it generates many other, usually infinitely many clusters on your space. And so when you do this, you perform cluster mutations, cluster Poisson mutations. It's different than in cluster algebra mutations or less. Wait a second. So you produce this infinitely many clusters. Then when you glue, so you produce a new cluster. How you produce this new cluster, I did not explain to you. That's why you asked the question. The rule is that on the sides which you glue, there are certain variables called frozen variables, and when you glue, you just multiply them. It turns out that this simple operation of multiplication variables on the side, this is the correct one. It gives you Poisson map. It gives you cluster because there is a procedure of cluster amalgamation, which tells you if you have two clusters here and you glue them, you automatically get a new cluster. There's a clear procedure how to do this, which you can, if you know that you multiply these variables, it's basically obvious how you introduce this new cluster after that. So gluing is a cluster operation. After I glue, I would be able to mutate this new variables I got. So I get actually a richer object, but okay. So very good one. Okay, so the major problem is this. So you have some modular space, and I claim that it gives you quantum group. If it gives you quantum group, Drinfeld and Jimbo defined quantum groups by looking at the Chevalier generators. Not all elements E, I, J in the Lie algebra, but only to Chevalier generators which correspond to simple roots and Cartan elements. So the question, okay, where are those elements here? And if you want to see them, the first question you ask, where are those elements if you just think about them as a functions? They should be visible. And it seems that they're not there. So it turns out that actually they are there. They're there immediately. And to see them, this boundary data is a key. So now let's introduce these functions. So I claim that there are, on the modular space PGS, there are some canonical functions, which we call potentials. They were introduced by Linhui Shen and myself in 2013, and it goes as follows. Here's a basic simple construction. First of all, is the group G is trivial, is adjoint, if the center is trivial, then this principal affine space, G mod U, I called it A, is actually moduli space. It parameterizes maximal unipotent subgroups U and non-degenerate characters psi of U. And any character canonically decomposed into sum of simpler characters, elementary characters, which correspond to simple positive roots. This means that we have U and R, where R is the rank of these simpler characters. Now let's suppose that we have a triple. And this triple is given by point of A cross B cross B. So it's a decorated flag and two usual flags, like it's a vector in two lines for PGL2 case. And we assume that A and B1 and A and B2 are generic. Then, because the pairs AB form a principal homogeneous space for the group G, if you have two of them, AB1 and AB2, then one is obtained from the other by a unique element of your group. And this element must be in the unipotent subgroup corresponding to A because you preserve the decorated flag. So this means that you get some element of UA. But on the other hand, you also have a character, and this collection of characters, which are part of your decorated flag. So now you end up with a function. So you just apply those characters to this element. And so the bottom line is that if you have a triple of flags like that, so this is A, B1, and B2, then there is this unique U, and there is unique function. This is W of U, W alpha I of U. So it's a function which you assign to this triple of flags. Now we go back to geometry of the surfaces. So suppose we have a corner on the surface. Then on this corner, we do have decorated flags. But if you go to the left, you see another corner and you have decorated flags there. And if you go to the right, you see another corner and you have a decorated flag there as well. So we can take these flags on the left and on the right. We can parallel transform them along the boundary to the point S. And then at this boundary point, we will see that we have this triple, because on the surface looks like that, but then you transform, you get the same kind of triple at your corner S. So you can apply previous construction to this triple, and you end up with a function. So given a corner, you have collection of functions, as many as the rank of your group, sitting as relate on this moduli space assigned to this corner. Even if your component had just one corner, you still can do it, because you take this decorated flag, you move it to itself from the left to right, and to itself from the right to left, you still get three flags, and you still have a function. And the same kind of spirit construction gives you these projections to Cartan group. Because if you have this corner, if you go to the right, there is another decorated flag. If you move it to this corner, you have pair of decorated flags. If you have pair of decorated flags, they produce element in the Cartan group, invariant of them. And then you can just apply roots to this element of Cartan, and you get canonical functions on this moduli space again. So the bottom line is that at the corner, you have R functions of one sort and R functions of the other sort. So W's and K's, potentials, and this kind of K functions. So this suggests that these functions, because they're defined naturally and by construction regular on everything on your moduli space, it suggests they should be promoted to quantum functions and produce element in the corresponding algebra of quantum functions. And this means the following, that you pick a cluster, and then in this cluster, because this function is regular, you can write this as a Laurent polynomial. And then you somehow want to promote this Laurent polynomial to quantum Laurent polynomial, which is not a well-defined procedure. But you also impose conditions that you can do this for all clusters and they're all mutation invariant. This is a very strong compatibility condition where it's not clear at all why this could possibly happen. And the theorem, which is kind of not trivial, it's a quantum Lipf theorem of Linhui Shen and myself, it tells you that you can perform this for all these functions. And therefore, at every corner, you have canonically these quantum potentials and the quantum K functions. Then you can ask the question, what kind of commutation relations between them? You can ask the question even on the Poisson level, what kind of Poisson bracket between them? And the answer is that you see precisely Q of B. that there is a map from UQFB which takes the Chevrolet generator EI and it goes to potential related to I's part of this function. And then the Cartan KI goes to this K functions which I just defined. So this has the same relations as in UQFB, the source relation. Okay, so this is if you have one corner, you get a UQFB. Let's suppose you have two corners. So if you have two corners, you always can ask what the commutational relations are. If they're far away, I claim they commute. But if they're related by an edge, they certainly do not commute and have some explicit commutation relations, which I don't want to write down. But I want to just discuss the most kind of special case when you have a component which has just 2 points. If you have 1 point, you have UQFB, but I claim that if you have 2 points, you have 2 UQFBs, and they live together in this modular space precisely as UQFG. Namely, assigning, so the picture is this. You have now a boundary component, and this boundary component has 2 corners. At each corner, you have EI here and FI here. You also have KI here and some other K here. And we prove that the commutational relations are precisely as in UQFG. Moreover, and that's important, we prove that this map is injective. So we have injections from UQFG for every boundary component which has precisely 2 corners. Then the question is about the coproducts. So where does the coproduct come from? So the coproducts always come from the gluing. And so the claim is that if you consider what happens with those canonical elements under the gluing maps, then they behave exactly as they should behave in quantum groups for the coproduct. So the gluing, quantum gluing is geometric origin of the coproduct. In particular, we get injective map of Hopf algebra in the situation I started from, when you have just this situation on log G, like related to this special surface. In general as well, but the special surface as well. And then the next question, so where are the other Chevrolet generators in quantum group? They're not quite there because you have to have Lustig break group action to produce generators which correspond to other roots, not simple roots. And this is not, it depends on some choices. And Lustig does this by introducing the break group action. The same happens here, and the break group action which Lustig has, it turns out to be precisely the break group action which I have geometrical in this moduli spaces. And so after that, we recovered geometrically kind of all features of the quantum group. Okay, now going back to history of the subject. So for PGLM, these elements were found by Gus Schrader and Alexander Shapiro. Although at that time we have these functions and they independently found these maps. And then the crowning kind of result of this business, which was proved by Linhui Shen, that for simple layers G, this map is actually isomorphism. So you recover the quantum group for the adjoint group G, just looking at this moduli space. Presumably the same true for non-simple layers case, but nobody looked at this. Okay. So far we covered the algebra. So we got quantum groups, we got them geometrically, didn't talk about R matrices, we got also the geometric R matrices. But now what about representations? So the main application of this cluster Poisson quantization that comes not only with algebra, but also with analysis. It produces you a representation of these algebras in a Hilbert space. How? So first of all, we start with this cluster Poisson variety. We do what we call Langland's modular double. This means that we pick a Planck constant h, any number. We make number q, which is exponent of I pi h, q check, which is exponent of I pi divided by h. And then we take quantum algebra for q and quantum algebra for q check. And when you do this for q check, if you have non-skew symmetrizable cluster Poisson variety, you can do this. You have to go to this Langland's dual cluster Poisson variety. But if you stick to simple laced case, it's just the same. And you tensor them. So this is my algebra, algebra A, which depends now on the H Planck constant. And you also have cluster modular groupoid. That's this, which gives this automorphism of this cluster algebras, cluster structures. So the objects of this cluster Poisson groupoid are just these Poisson clusters, meaning just coordinate systems. And the morphisms are generated by mutations and also by isomorphisms of clusters. So you get some groupoid, and its fundamental group is what we call cluster modular group. And so the previous theorem just means that this group gamma GS, which I described geometrically, is a subgroup of this general cluster modular group for the example. Okay, now we go to quantization. First of all, if you have a Poisson cluster, there is a Heisenberg-Lie algebra related to this, obtained by taking logarithms of those coordinates, little xi. The Poisson brackets between them is 2 pi h epsilon ij, so this is a Heisenberg-Lie algebra. Then it has canonical Heisenberg or Schrödinger representation by unbounded operators x chi hat in some Hilbert space. That's exactly what quantum mechanics was doing 100 years ago. And if you choose h bigger than 0, I can choose them to be self-adjoint. And then the point is that this Heisenberg-Lie algebra produce you, in particular, this big algebra A, this modular double, because you can take the exponents of these operators, they're self-adjoint. You can exponents of these operators, and you get exponents of them divided by h. And they commute on the nose. That's a property of this modular double, that xk and xj check commute. This means that you have representation, action of the tensor product of these two algebras, and that's exactly the definition which you see here. You have tensor product and x by this operator and that operator. Now, this is unbounded operator in the Hilbert space, so it doesn't quite make sense. So you can ask for the common domain of definition of these unbounded operators, and that's by definition the cluster Schwarz space, S. And now the key thing. So far we were doing basically quantum mechanics 100 years ago, but so now we have, so far we just have kind of Darboux coordinate systems and we play with it. It's very simple. But now we do something new because we now have this nonlinear mutation, nonlinear transformations. And the main claim is that you can quantize mutation. So this means that if you have any mutation, you can produce some unitary map from the Hilbert space of related to one cluster to Hilbert space related to the other cluster. And this map is basically given by this quantum dilogarithm function. So let me say a few words about it. So this function was introduced by Barnes 100 plus years ago, then rediscovered by many, Baxter, Fadeev, and many people. You're right, Vanya. Not only mod q equal h is real unitary, h has absolute value, 1 is unitary, and there is a regime when h is imaginary, also will get unitary. I'm not talking about this. For me, it's enough to have h is real, and therefore q is absolute value 1. Yes, good. And so now I consider this function. It's given by some integral. But on the other hand, remarkably, this function is just the ratio of these two quantum dilogarithm power series. One is related to q and the other for q check. One is argument is exponent of z and another is dual, exponent of z divided by h. So it turns out this is an equality. And what I'm doing now, I'm using analytic properties of this phi function. The analytic property is such that, for example, if you're on a real line z and model q is 1, then you get complex number of absolute value 1. But most importantly, this is a well-defined function. So you can apply this function to any self-adjoint operator, and that's the definition of this quantum mutation. So I realized that I didn't write it. So the formula I was alluding that the quantum mutation is given by the operators as phi h of the operator little x k bar. So it just applies this unitary operator, and it produces you map from your unit Hilbert space to itself. And then there is a little linear transformation, which I like value representation, which I omit. But now, why it's compatible? So the result is this, that for any cluster, I can introduce this Hilbert space and this data. If I have two clusters, I have some unitary transformation. And the key property is not only that it's unitary, but it transforms Schwarz spaces to Schwarz spaces. And because of that, I can ask the question how it works, how it relates the actions of my algebra A. And it turns out that this is an intertwining operator. And I claim that this is basically obvious if you look at this formula 3, because in this formula, on one hand side, I use integral to define the operator. On the other hand, this is ratio of this power series. And the denominator is going to commute with all elements in OQ of x because it has just z divided by h. So what remains is the numerator. And the numerator was the way I defined quantum mutations in algebra. So this algebra and analysis, they agree because of the two reasons. That this nice analytic function is the ratio of two power series, and that the second, the denominator, simply do not act on one factor of this algebra. And also, to finish with this discussion, this is very interesting ratio because neither numerator nor denominator are well defined when absolute value of q equals to 1. They both divergent. But their ratio is very beautiful analytic. And also relates to the logarithm when h goes to 0 or rational. So we have now a machine which allows us to take some cluster Poisson variety produced to the corresponding algebra, and this algebra is represented in the family of Hilbert spaces. So that's what I call cluster quantization, and it provides this representation which I call principal series representation. So the cluster feature here is that there is no preferred vector space, because vector space corresponds to cluster, and cluster is never given to you. You have to choose, no clusters are better than the other. So you have a groupoid of vector spaces, and they're related by these quantum intertwiners. So that's a structure. There's no vector spaces canonically. I mean, just single vector space. And then there is a structure of tensor product-like structure, which corresponds to gluing. And so if you do this for Poisson-Lie groups, then what you get is family of representations which behave like they form a continuous monoidal category. Okay, so that's a kind of cluster representation theory in general, but let's see what happens in the example when we have UQ of G. In this case, I should remind you how the classical representation theory goes. Classical meaning principal series representation, Gelfand-Nymark series representations. So you get representations V lambda of the real Lie group G, which is realized in L2 of principal affine space, just by decomposing this by the right action of the Cartan. And we know also that representation related to characters lambda and W of lambda are equivariant. And we also know that actually equivariant in a canonical unitary way. This is a Gelfand-Greif unitary intertwiners 50 years ago. And we also know that if you want to consider tensor products, we again have a nice model because this is just L2 on the products of affine, principal affine spaces. And we can take model for invariance, and this will be L2 on the configuration space, which is G orbis on A to N. The last comment is important for the future. And the claim is that it looks accidental that in this case, this configuration space which we get for G invariance is nothing else than our moduli space which we assigned to N1. Now let's go to the quantum version of the story. In the quantum version, we have the space of G local systems on decorated surface. And so by general machines, they produce this principal series representations, in this case of the algebra of functions, which is UQ of G, at least UQ of G is signified there injectively. And they're parametrized by the same data, which boils down to linear function on the Cartan-Lie algebra. And the Weyl and Red group action as unitary intertwiners, and the Weyl group action is a quantum analog of Gelfand-Greif intertwiner. So it proves that these representations at lambda W of lambda are equivalent. And now comes a claim which I'm going to state but not to explain. So it follows from general principles of this story that if you consider the invariance with respect to quantum group of this principal series representations and take integral of all of them with respect to lambda, then the space which you get should be canonically identified with the quantization space of sphere with n punctures. And so look, so we have in quantum situation quantization of the sphere with n functions. And this gives you a model for invariance. In the classical case, we have a similar space of invariance, and it gives you functions which you see on the left in configuration space related to hexagon. So this is classical, this is quantum. How they are related? So they are of different nature. This is L2 on the space, and this is quantization of entirely different space. It turns out that there's a general principle, general construction, that if you take that you can do the following. You can take any decorated surface, for example, hexagon, and you can double it, just putting surface and the opposite surface, making a new surface. So in this case, if you double hexagon, you get sphere with 6 punctures. And the general claim is that representation of algebra related to the quantum to this kind of double can be realized in a natural way in L2 functions on the moduli space related to the original surface. In particular, if you do this in this case, you see that invariants for the quantum group representations are realized in L2 in the configuration space for this principal affine space. And that's exactly where invariants were sitting in the classical space. So now you start to see that this quantum and classical story fit together. And so that's I recorded here. And so now I wanted to say that it's a very interesting space of quantum, of invariance in quantum tensor product of this representation of UQ of G. And this space actually appears in 3 different ways. And the claim that they are all the same is the analog, conjectural analog, continuous analog of this Kazhdan-Lustig theory. And here's how it works. So if you take a Lie algebra G, it's known that it produces you W algebra, WG, which for GSL2 gives you Virasoro-Lie algebra. It is also known that thanks to Fagin and Edward Frankel, it produces you a family of unitary highest weight models for W algebra, well known, of course, for Virasoro algebra, which parameterize by exactly the same data as all these lambdas, linear functions on Cartan. And then if you take these W algebras and their representations, you can put them at the punctures of a Riemann surface and take coinvariants. So you get some vector space. On the other hand, this vector space depends on complex structure because coinvariance depends crucially on complex structure on this surface. And so when complex structure moves, they move. But now you can consider the topological surface underlying this Riemann surface. And as I said, there is a cluster quantization of Z. So that's another space, Hilbert space and Schwarz space. So it's a second space. It produces Schwarz space and it depends on the same kind of data, alpha. And the main conjecture is that the space of coinvariance and the Schwarz space are sort of the same. But if you try to say that they're the same, this is definitely and absolutely cannot be true because the space of coinvariance is kind of has filtration quotients, finite dimensional, it's kind of discrete space. The space which appears in cluster quantization is Schwarz subspace in the Hilbert space, very different nature. And so I say that what should happen is that there should be canonical non-degenerate pairing between the spaces, which is continuous where it could possibly be continuous, meaning on the second component, because that's where you have topology on the Schwarz space induced by the Hilbert structure. Because it's non-degenerate and continuous, it gives you map from the coinvariance to the distributions, cluster distribution space. Now on the left, you have vectors which are parameterized by this kind of data, and among all of them, there is the most important one, the product of highest weight vectors, because this W are highest weight representations. So if you take this highest weight vector, what? Just read what is under this formula. That's exactly the statement. So if you take this highest weight vector, and then you map it to the space of cluster distributions, you're going to get canonical elements there. And there I say that it's supposed to be the Toda theory conformal block, which for SL2 is supposed to be the Liouville theory conformal block. And so the bottom line of all this is that we have 3 kinds of spaces. The main of them is given by cluster quantization, and it relates the other 2. The other 2 are either coinvariants of principal series representations, and then they're related to this one by this conjecture, or it's coinvariants of tensor products of representation of the quantum group, and they're related by general principles of this business. And since both 1 and 2 related to 1, they in particular should be sort of related or almost isomorphic. And that's what I call this continuous analog of Kazhdan-Lustig theory. Because Kazhdan-Lustig tells you that something like that is true when you're talking not about continuous principal series, but about finite dimensional representations, what you get from them to Kac-Moody algebra and therefore to W algebra on the one hand side, and tensor product of finite dimensional representation of UQ of G. So here we have principal series for UQ of G, and this principal series for W algebras, and the connections that you try to explain, and it goes through this cluster quantization. And finally, actually, the time is over, so let me stop here.
Thank you, Professor Goncharov. Any questions?
Maybe it is written. Next page it will be exactly the answer to my question. But let me recall what you did with Volodya Foka. It was quantization. It was GLN, I know, and no G equivalence, right? His answer was fantastic.
Gamma. The gamma equivalence was there.
No gamma equivalence.
Absolutely gamma equivalence. The story is empty without this.
When the relation appeared, T25 equals 1.
As this is related to gamma equivariance. This pentagon relation in one of the things you have to check to claim. It's related to checking relations in the modular groupoid. So this
one, right?
No, this was about cluster quantization. To get quantum groups, you have to apply this to just one particular surface, or the other particular surface if you want to take another. I wouldn't say everything was already there, because the key part of this definition, that we end up with a definition of some moduli space, which is correct, in the sense that it can be glued and has all this boundary data. Again, I'm never talking about G-local system per se, I'm talking about this boundary data. Boundary data gives you a way to glue and gives you these functions which produce all these quantum group elements. And we have some moduli space very closely related, but not exactly.
You mentioned today that without boundary data, it is not that interesting. So it will be very much simpler.
No, it's not. It's interesting. It's just some bits of not that much is missing, but it's just something will be missing. So no, in the work with Fock, we have a lot of this picture, but not completely. And we didn't have the theorem about cluster structure, which is much more difficult for any group other than GLN. Than for GLN. For GLN, we have some kind of gift that there is unique cluster which is kind of Zimos through the invariant, and there is nothing else to prove about this. And not the case for any other group.
Thank you. Of braided monoidal category.
That's the one I'm talking about here.
So I'm asking if you have an idea of what sort of categorical structure.
This is this kind of continuous analog of monoidal structure I was talking about. That's precisely it. Yeah. It's not a category because it's now objects are parameterized by continuous data, sums are integrals, but other than that, if you...
Basically, there is no more concise way to say.
Huh?
There's no more concise way to describe the structure.
No. You have to say that you have this, instead of, you talk about this invariance and so compatibilities and so on. When people say category, they mean category. It's not a category. I mean, this is not category per se, so it's similar to category. It's similar to monoidal category. It's not category per se. Yeah.
The degenerate symplectic structure on the symplectic group, Poisson structure, on the symplectic groupoid of upper triangular bilinear forms.
Yeah, so yes, famous, yeah, go ahead.
Does it fit? I mean, is it Poisson cluster?
It's part of the story, yes.
Yes, but the symplectic structure on the upper triangle bilinear form themselves is not, right?
No, this story, I didn't discuss this at all. All this cluster business story, it actually comes, cluster varieties comes in pairs, so even better to say and relevant to your groupoid and triples. And so I just discussed the Poisson one. There is a one which relates to cluster algebras, which is K2 symplectic. And then there is the most interesting one, which is the double of the original Poisson. And this kind of data relates to your groupoid. So your groupoid appears when you start talking about this quantum symplectic double of something related to this original Poisson variety. But it's a long story to discuss.
Thank you.
Get some analogs of KZ equations for these spaces of co-invariants there.
There is no, so the point is this, that on the space of co-invariants, there is a connection, sure. This connection is not integrable because the fibers are infinite dimensional. It's this fibers is like if you take model space G and then take a point and take the germs of functions or maybe like Taylor series. So of course it has connection like on jets everywhere, but it's kind of used, but it's not integrable at all. Yeah, of course it's Liouville, it's not KZ. The question was about analogy.
Yes, but some Liouville blocks also satisfy KZ
But-
equation.
But no, this is when you put degenerate representations. We are not talking about this. This is degenerate situation. But here there is no parallel transport, but there is mapping class group action still, because the mapping class group still acts by construction on this quantum cluster quantization, and there is a way to explain that they are compatible. There's no contradiction. I'm not doing this, but there's no contradiction, although you cannot integrate that connection. Nevertheless, the very fact that I claim there should be this canonical pairing, if you think about this, I can explain, you naturally see that if you go around, you get precisely the element of the modular group action which you get by this construction.
That's a question? So if no, let's thank Professor Goncharov.